Bless you.
All right. So let's see, they got, let's see, does that picture go with this from? Is that the one? No, it's the one before.
Yeah.
Points A and B are separated by a lake. Four little points A and B. To find the distance between those, surveyor locates a point C on land such that angle CAB is 48.6. Okay. Blah, 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 blah. So so this angle here, angles, so wait, no, CAB, so it's got to be like this. That's a very strange thing. So here's C, so he's saying CAB. So it'd be 48. So I don't know if you guys remember when you say CAB, the one in the middle is what really determines where it is.
Well, I didn't know that.
That's why I drew it home the first time. Cab keeps you straight. A is in the middle. Because I had A, C, B.
I didn't know that. And there was nowhere where it said it.
Oh yeah, C, A, B would have worked too, yeah. All right, I love you guys. So C, A, B, 48.6 degrees.
I just wonder over there now that there's a...
Well, he also measures CA as 312, CA is 312 feet, and CB is 527.
CB. That's it.
CB. Thank you. Oh, I see. So I see what they're trying to say. 527. Find the distance between A and B. Okay, cool.
Well, that makes it kind of easy now. It's just,
Yeah.
I didn't know that CAB, I didn't know where it's supposed to be, angle was supposed to go. I put it on C.
Yeah, they give you pictures for problems that you should really be able to set up yourself. And then this problem would have been really nice to have a picture for. Because actually, the way I've drawn it is a little wrong. C should be over there. Here's A and B, separated by a lake. C, I can actually walk off these distances around the lake, right? So then CAB here is 48.6 degrees. So what's, now of course the section you're in kind of gives us away very often, but what situation am I in? What can I use? Well, I mean, this is interesting because they have, I mean, can you make what tells you that you can use law of sines? What tells you when you use law of sines?
You have an angle on this.
Exactly, I have an angle and its side. So I have an angle and its side. So I can make that ratio. That's what tells you you're allowed to use law of sines. This is number 36.
Correct, 6.5.
6.5. Alright, so cool. Good enough to get started? Okay, good. Let's see. Anything else from homework? Yeah.
39.
Uh-oh. Couple in a row. A tree on a hillside casts a shadow. Let's see. Let's go with this. So here they give you a little picture. This is a little bit freaky, so it's good to do that. A tree, so I know this is 22 degrees here. Here's your tree. Woo. 215 feet down the hill. So this distance here is 215. If the angle of inclination of the hillside is 22 degrees, that's sort of like angle of elevation. Right, so the angle of inclination. Normally you can't be standing where it is, but it just means the same thing as angle of elevation. Cool. And they give you that inside, 22 degrees. And the angle of elevation of the sun is 52 degrees. What's up? There they are. So here's the sun, and its angle is bigger. 50, what did it say, 52 degrees? Where did this problem go? There you are. 52 degrees. Find the height of the tree. I like it. 215, yeah, I got everything right. 22 there. And 52 there. Okay, cool. I like it. And of course, my picture is horrible. It really should be here so that the shadow makes sense. There's the sun there. Now the shadow makes a little more sense. Okay, so what have you got going on here? You've got how many right triangles you can play with? Two. Beautiful. What else? You only know, let's see, we know for this little right triangle here, we know an angle and a side. Then I got this weird triangle here.
30.
Yeah, so this angle specifically is 30. Should we have another color? No, not today. So this angle here, it's got to, of course, be the leftovers, 30 degrees. And that's a nice triangle because it includes what? What's the question? Height of the tree. And that triangle actually includes the height of the tree. That seems promising, right? So this is what I want to know, this height here. So that triangle includes that information. And I've got a side here, and I've got an angle here. Anything else that I have? Do I need anything else? Yes?
Well, the whole triangle, like you have the bottom, the base, which is 90 degrees.
Good. So this is 90 here. So then you know
The tree, so
this.
38.
Beautiful. I love it. So the problem was, if you looked at the triangle, it actually was including what the question was asking for, the height of the tree. I only had an angle and a side, and that's not enough to do anything. You don't have anything that's used for sa, right? Sa, not sa, S-A-A. This is, so right now it's just side and angle, but now this whole thing is a right triangle. This angle here has got to be leftovers from 5290, so that's going to be 38. I like it. So let's kind of focus on that triangle there. There's a lot going on there. So I've got, this is the tree. This is what I want to know. This is the 215. This is the 30 left over from the two angles they gave me. And what am I leaving out?
38.
Well, we just figured out, yeah, 38 degrees. So can you see a ratio that you can complete? Yeah, cool. You got an angle with its side, and then you got the angle with the side that you actually want, which is nice. Cool. And of course, we could figure out that last angle if we wanted to. We don't really need to. Yeah.
42.
Is that enough there? Is that good? All right. 40 what?
42.
Oh, we're just going to work our way. Okay. I like it. All right, let me see. Let's see if we can get this started. 42, the one about the water tower?
Yeah, that one didn't make any sense.
Absolutely no sense. Okay. A water tower 30 meters tall is located at the top of a hill. Oh, water tower, what? What did I say, 30 meters? From a distance of 120 meters down the hill, it is observed that the angle formed between the top and base of the tower, blah, 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 blah. So somebody's standing 120 meters down the hill. Let's make my hill a little bit more cooperative. So he's standing right there. And he notices that the angle between the base, let me make it very small, there. He's laying on the ground. Between the base and the top is 8 degrees. Thank God you have the picture in the book, if you have your book. Because I am not an illustrator by any means. And it's 120 meters down the side here, so if we focus on this little triangle we have going on, there's the tower. This is 120 meters down, and this angle here is 8 degrees. Oh, and this is the tower, of course, is 30 meters tall. That's nice. And then they want you to figure out the angle of inclination of the hill. So where is that at? Where's the angle of inclination of the hill? Where is that?
And that's the parallel line from the bottom up.
Yeah, it's the horizontal at the base of the hill. cutting through. So what we really want is this angle there. So in a way, does that feel like the reverse of this one?
Yeah.
In a way that we had 22 degrees at the beginning, we didn't have the height of the tree. This one, we have the height of the tree, the tower in this case, and we don't know that angle, that corresponding angle over there. Bless you. That's as far as I'm going to go. Because if you do this one all the way out, your math should look similar in a lot of ways to what you need over there. Here you just have an unknown, where here you have 30 meters. You actually know what the height of that thing is. Is that enough to get you started? Whoever asked that?
Yeah.
That's enough to get you started? Okay. Yeah.
And also,
45.
having trouble with
Oh, yeah. Yeah.
the 19 to 28, using, like, solving for all the triangles. Can you go over, like, 21, 24, or 27?
All right, let's look at 24 here. So when you draw this, you can make your triangle any way you want to. It doesn't really matter. Doesn't even have to correspond to the lengths, because again, you have a third dimension. You just say it's leaning away from you or leaning towards you. You don't have to draw it to scale. Let's see, where to go. A is 75, B is 100. And let's see, what else do we know? Angle A is 30, so where's that going to be?
Across from.
Yeah, across here, this is 30. And then they want us to solve this triangle? Yeah. All possible triangles. So what is it that you have to... And again, I always try to give you a different way to look at this than just memorizing the SAS or whatever it is. And of course, it's ass, it's the ass. But in general, anytime you have to use what, you have to be careful. Anytime you have to use inverse sine to find an angle, it could possibly be just a reference angle for another triangle. So in this case, I only know one angle. So it's really, when you only know one angle, you're going to have to use an inverse trig to get another angle. So you know that there could be two triangles here. And I think this one, no, not this one. There's at least one problem in the homework where it's an impossible triangle. You can pick up on it pretty quick. Or you can do the work and it comes out. If you ever get to this point here, what's wrong with that?
You can't have a sine.
Yeah, you can't have sine bigger than 1. Right? I love it. It's like somebody in my stats class telling me the probability is 114%. This one's going to go, holy crap. That is so going to happen. It's going to happen next door too or something. I don't know what that means. So, if you can get these, this is going to be nice. This is just a straight up no physical problem. You're not looking up at a mountain. You know, this is just straight up. What ratio can you make?
No.
Yeah. So for example, what's the ratio you can make that's complete?
Sine.
Sine 30 to 75.
And then you definitely want to relate that to angle what?
Sine.
Yeah, B, because B, I know B is psi. I don't know crap about C. So I'm leaving him to the end. I don't know nothing about it, right? So that's the ratio you can totally make, and then this is the ratio you can partially make, and then you just solve for B, get your inverse sine. Can't remember. Let's do this. You guys figure out what inverse sine. Figure out what B is if you haven't done this problem yet, and let's check to see if there's another possibility.
41.8.
Do it more. I'm sorry.
41.8.
41.8. Okay. So verify that's true. Do the inverse sine stuff.
So there is a possibility.
Yeah. Because what would this? So this could be B1. What would B2 possibly be?
138.
Yeah, 180 minus this. This would be a reference angle in consideration. 180 minus this, so 138.2. And does that fit with the angle I know?
Yes.
Meaning, if I add those, is there something left? Yes, there is. It's 168, so there's plenty left for the last angle. So you're going to have to do two triangles and be really clear in your work. Label things 1 and label things 2. Keep them separated. Make it very clear to me what's what. So do this one all the way. So now that we know B1, you could figure out C1. Once you know C1, you can make the ratio with this little C dude. Right? And you go from there. Does that make sense? Once you know one more thing, everything kind of like falls into place. Yeah.
So solving for two triangles within a triangle can just It's just, your initial answer and then the secondary answer is 180 minus your initial answer.
That's what gets you started, right? Because a complete answer here would be angle B, angle C, side C. Because that's the stuff I don't know to begin with, right? Angle B, angle C, side C. Those I don't know. So I better see the same thing. I better see angle B, angle C, side C. You got to figure that out for the second situation. You got to completely solve it in both situations. I like it. Maybe. Okay. Cool. Anything else from homework? Have I gone through all the word
No.
problems? Okay.
6-6, number 18.
Well, that's the one. Number 18?
Yeah, 6-6. 6 or 6-6.
Oh, wait. So here's another one. They just give you the lengths of the sides and the angle. Let's see. So they tell us A is 65.
C is 50.
C is 50. And angle C is 52.
Yes.
Okay. So again, it doesn't really matter. You can be a little careful if you want to be. There, we'll make that A since it's the biggest so far. So we'll say this is A. This could be C. So this is angle C, angle A, angle B, side B. So that's the first step, is just setting up your triangle and labeling everything appropriately.
40.
Obviously,
52.
52 for C. Thank you. If you put something in the wrong place, obviously going to screw the whole damn thing up. So you got to be careful on the first step. Make sure that the angle across actually is the right one that goes with it, based on their symbols. And then from the very beginning, I knew this is the ratio I could set up completely, right? I know it's angle, I know it's side. So I can use that to figure out, what's the first thing I can figure out is angle A, because I know A is side. Is that cool, Chris?
So is there any way of doing this? Now, I'm aware you could use the signs on this one, or, well, maybe. And I know a possibility of two triangles exist, but being that this is in the cosines, law of cosines section, is there any way of doing this without the law of sines?
Well, let's see. Do I know... What do you always need for the law of cosines?
Two sides.
Yeah, you need
Two sides and an angle.
two sides. So let's see. Do we have enough?
Yeah, but
If I
see,
did,
Good. On the other examples and stuff that they give, the unknown side is usually the side with the angle. So basically, C would be the unknown, B would be known, A would be known, and C.
I know that's for law of
So-
cosines. Exactly right. Because what I'm about to point out is, not only do you have to know two sides and an angle, but that angle pretty much has to be,
In between them.
yeah, the included angle. Yeah.
In the on web assign it says use law of sines or cosines. Just so.
Yeah, I mean, once you get into section, and we know this about math, right? You got to be a little careful. I know section 6.6 is law of cosines, but now you're past section 6.5 where you learn law of sines. They start to mix it up a little bit in section 6.6. You know law of sines, so you use it when it's appropriate. And when is it appropriate? When you can actually make that ratio. Not very often, unless you knew more than you normally do in these problems, would you be able to use either one. They'd have to tell me what B was also. If they told me what B was also, if they said B was, 48, then you can use sides or cosines.
Preferably cosine. Yeah.
Yeah, obviously preferably cosines.
Yeah.
Because then you don't have to worry about, is it a reference angle or not? Right?
I've got some stuff I'd like you to look over a little later after class practice.
Sure. Yeah.
Number 30. Same section. It's the triangle formula. It's talking about it.
Oh, yeah. That's right.
I think it was actually number 30 on homework. but
So in this section, they give us,
Heron's formula.
yes, Heron's formula. And actually, it's kind of nifty. I mean, I would love to create a history of math course where we talk about all the contributions of all the different cultures and where things evolved. Because when you learn math, you don't learn it in chronological order. Sometimes we'll learn something that wasn't discovered until way after stuff we learned later. We just teach it in the way that makes the most sense now. So sprinkled throughout this section especially, there's going to be a little historical kind of things that people have discovered. So this is one of them. They give you this formula here. Where the triangle is here. Nothing weird about it, right? And they tell you that this little S dude is what's called the semi-perimeter. I appreciate that. It's like the perimeter just cut in half. So it's perimeter A plus B plus C cut in half. So the reason I sometimes don't even talk about these things is because, back in history somebody did a lot of work to get here. But now, what is this really? Now that they've done all that work, we can just apply this. We can just use this. So for the triangle they give you, figure out the semi-perimeter and plug it in. So the triangle they give us, number which one?
1, 2, and 2.
Yeah, 1, 2, 2. So 1, 2, 2. So you get 5 halves for S. So it'll be 5 halves times 5 halves minus 1 times 5 halves minus 2 times 5 halves minus 2. Cool? I mean, that's just a plug and shove now. That's it. That's all. Nothing major. Another reason why I do that, and sometimes I'll do this on purpose and sometimes I just forget. But this one I definitely on purpose skipped, just to make you look back through the section to see what the hell's going on. How the hell am I going to figure out the area of the triangle? It's not even a right triangle. How can I do that? Well, there you go. You use this formula. And I don't think they give you any background. Oh yeah, they give you the proof. It's right there. It's beautiful.
Number 30.
What about
I don't
30?
know. It was on WebAssign. Dude, I just gave him an example.
Yeah. So section 29 through 32. Those problems. Yeah.
Last homework question, number 46. Same section. Airport A, Airport B.
Oh yeah. Okay.
6.
So airport B is 300 miles from airport A. Where'd he go? 300 miles is 50 degrees here.
You got it.
Blah, 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 blah. And this here, you can kind of tease out the meaning of this if you're not. This is bearings, 50 degrees east of north. So here's north, 50 degrees east of that would be there. So it's not quite true northeast, it's a little bit further. True northeast, of course, would be
17.
right in between north and east is what angle?
Northeast.
Look, 45 degrees.
Yeah.
Cool. So it's a little bit further past northeast. It's more east than northeast. Somewhere in there is a Hitchcock reference. The other way. Blah, blah, blah. Oh, good. This is a little bit freaky. A pilot wishing to fly from A to B mistakenly flies due east at 200 miles an hour for 30 minutes. Well, that's stupid. I hope they're not flying my plane. So this dude flies this way.
For 100 miles.
Exactly. You got to be careful. I graded a couple of those papers where they put 200 here, but he flew 200 miles an hour for 30 minutes. So it only went 100 miles in the wrong direction, sort of. Part of his direction was right. When he notices his error, he's flown over the wrong airspace, and things bad are going to happen. So how far is a pilot from his destination at the time he notices the error? So they've already, this is so funny, this is the picture they should have let you make. But, I mean, so obviously this distance here is how far away he is. Yeah. There's 100 miles. So to work this bad boy in, of course, into my triangle, that would just be
That would be 40.
40. Yes, ma'am.
Why is it 100 miles?
He's going 200 mile an hour for half an hour. Cool. So be careful. It's not 200 there, it's 100 miles. So he caught it only 30 minutes later. This is your captain speaker. I'm a dumbass. Okay, so how can you figure out this distance here? Call it D.
Cosines.
Yeah.
Yes, perfect. You see that we know
And
these two sides and that angle. Beautiful.
That wasn't the hard part for me. It was the-
Oh, okay. So that's part A. Part A is easy enough. It's law cosines. Law. What bearing should he have his plane? Oh, I love it. Okay, cool. So now you want to figure out, to get here, what would this angle here be? Right? He should have been going 50 degrees east of north this way. But now what's he got to do? How many degrees east of north does he have to go? It's going to obviously be how related to 50.
Why would it be related to 50?
If he went a little bit further, he would have went just straight north. It would have been north 0. Wouldn't even put 0 in there. Just say north. You guys, you see what I'm saying? It's flashing over there.
So what about finding that whole angle and then subtracting the reference angle from it? Or not the reference angle, but 90 degrees.
Finding what whole angle? Oh, this here. Yeah, of course. Yeah. So all you got to do there is figure out that angle. And this is pure north and this is pure east. So you know this is 90 degrees here. So if you know this whole angle, you just have to subtract that whole angle minus 90 degrees. See what the leftover is, right? Beautiful. Sweet. Anything else from homework? I think it's plenty. Alright. So, we are now going to do some derivation, which means it's nothing I would expect you to do on your own. It might be somehow related to a bonus question I can give. Use between a pseudo. Actually, I didn't use this one. Easier. All right. Thank you. You are Panasonic. So the book has a way of proving this. And to me, it was just lacking. But just so you're keeping up, I'm going to talk about this, and then we're going to get into doing some examples from 7.1 and 7.2. So we just barely started talking about 7.1 last time. But I want to give us a few more identities to work with. Here we go. So if what I want to investigate is these two things. This is alpha and beta. I just want to put those down because the book uses those sometimes. And that's what you kind of use. Instead of theta, you very often use alpha, beta, gamma for angle names. So I want to figure out what sine of alpha plus beta and cosine of alpha plus beta. I want to know what the hell those are in terms of simpler things. Okay, so what I've done here, and this is not just me, what I did was, there's a triangle there that involves beta. Beta is in the base, and I made this 1, so that was nice and easy to talk about. But I also want to have a triangle, a right triangle that's got alpha in it. Let's put this thing. It's in 2 different places. I love it. All right, we'll be all right. Just so you know the title of what we're doing. So this triangle down here has got an alpha in the base. This triangle by itself has got beta. And of course together they make alpha plus beta. So somebody help me out here. Here's the 1. Let's start with this. This is the hypotenuse of 1. Here's the right triangle for this dude up here. Right? Alright, so I just want to see what we can figure out. So what is the angle involved? Let me pull it down here. It might be easier to look at. Is that cool? If we do it like that. So it's beta we're talking about. That alpha plus beta is all together.
Yeah.
So can anybody tell me how long this here is? How long is
What's
this?
alpha plus beta?
Again, let me see if I can do this. Let me take this out of the way. This is beta, and this is alpha. So together they're alpha plus beta. So the one we're looking at right now has only got beta in it.
Sine of beta.
I love it.
Over that.
Yeah, sine of beta equals this length divided by 1. So this length is sine beta.
Yeah.
Cool. Yes, ma'am.
If this problem were to come up, how can we make the assumption that that angle right there above the rectangle is a right angle?
Sorry?
Well, like if you wrote
No. I created it. I made it a right triangle. So what I'm doing, if I want to investigate what sine of alpha plus beta is, and I know that sine and cosine are all sides of triangles, and I really want to base it on what sine of alpha is and cosine, and I want to kind of tear this apart somehow, right? So what I'm going to do is I'm going to make a right triangle for beta by himself, a right triangle for alpha by himself, but I'm going to set them up so that I get alpha plus beta in the same thing also, when the big ass triangle's got alpha plus beta in it. So the setup was completely me. I forced this bad boy to be a right triangle. That's how I know he is. Now if I gave you a triangle, what would I do? I'd tell you the damn thing was a right triangle. I wouldn't.
Okay.
Right? If I wanted you to do stuff like this, I'd have to tell you this is a right triangle. There's no way in hell you would just go, well, that's obviously a right triangle. No, there's no way you can know that. So, I mean, on that level, that's a good question, but also I just forced it to be so. Because now I can use normal, basic trig stuff to figure some sides of this triangle out. And at the end, I want to get alpha plus beta. So I'm going to look at like total side lengths and everything else to see what this thing is in terms of other things. So right now, this right here is just sine beta. So what's the base here? What's this? Don't overthink it.
1 minus.
Sort of, sure. But what's the better way to say that? Cosine beta. I like it. That would work out. There's nothing wrong with that. Alright, how are we doing so far? I really want you to realize this is really just our unit circle work, isn't it? If I was given a radius of 1, the y piece would be sine beta and the cosine piece would be cosine. I mean, the x piece would be cosine beta. We just stuck those on a triangle now to be a little bit more specific to the situation. So what about this triangle down here? What can I talk about for it? How long is... here's where things get interesting. I had to start with this triangle here. Why? Why did I have to do this triangle first? Did I just do it just because I had to do one of them first, or was there a specific reason?
Because you know the...
I knew from the beginning.
Yeah.
Now I know how long this guy's hypotenuse is.
Yeah. Cosine.
This hypotenuse is cosine beta. Yummy. So how long is this?
It's sine
One
alpha
sine of alpha.
over cosine beta.
So let's see. It would be alpha. It would be sine alpha equals. We'll call that y for right now. Is that cool?
Yeah. Over cosine.
I know some of you guys have already tuned out. There's no way I can force you to tune in. You just don't have that mind power. But just try. I'm not going to make you do this on your own. I just want you to try and grasp what's going on here. We're going to get to a point where we have identities that we can use, but I desperately want you to see see why it makes sense where they come from. So yeah, y sine alpha would be
Sine.
y over
Y over cosine beta.
y over cosine beta. So of course y is
Cosine beta times sine.
sine alpha cosine beta. I love it. Let me let you absorb that. So if I know somebody's, I really want you, I keep saying this, if I know the hypotenuse, then the y and x side are easy. It's just the x side is cosine of that times this, and the y side is sine of that angle times this. Right? It's just like sine and cosine are percentages of the hypotenuse. So what percentage of the hypotenuse is along this side? Sine alpha times it. And what's on this side? Cosine alpha times. So how long is this whole base? What's this length here?
Cosine.
Cosine alpha, cosine beta.
How'd you get there?
I don't know. Let's see. What's cosine of alpha by definition? Cosine of alpha, what would that be?
Cosine
It
alpha.
would be cosine alpha is
Cosine beta.
x over cosine beta. So what's x? Multiply that up. Cosine alpha, cosine beta. Let me stop right there for a second. It's free. But if this were 7, then this would be 7 times cosine alpha. This would be 7 times sine alpha. That's how quick it is to break up a hypotenuse into an x side and a y side. How we know so far? We're going to get to very freaky little phrases, little expressions. We're not used to this. This isn't anything in general that's going to happen. This is just for this setup. But we are going to get a general equation out of it, a general identity out of this. Anything else I can figure out from this weirdness? See, am I forgetting anybody? It's about, oh, well, let's see. There's one more thing at least.
Is it good?
How big is this angle here? Take it down there.
180 minus B.
90 minus beta. Yeah, 90 minus beta. So this whole thing is 90 minus beta. You stop right there for a second. So look at this triangle here. If that's beta, and that's 90, this last angle has to be 90 minus beta. It's got to be the leftover, right? If this was 90, and this is 20, that's got to be,
7.
which is 90 minus 20. Oh, it's got to be the leftover of the, this 90 needs another 90 total, so this would be 90 total so far. How we doing so far? You guys all right?
I'm still kind of back on the cosine.
And this is something you do. You already do. You've done this. You just haven't looked at it with weird-ass symbols. Yeah, but you've done that same work. Numerically, you've done it. Can anybody tell me what this angle is? This angle right there.
90 minus A minus B.
Cool. Why? Who said that?
Because
You kick ass.
data and alpha are the
Because now, what triangle is that little angle in? What right triangle is that little angle in? This whole damn thing. This giant one, right? So this is the 90 here. This is alpha plus beta. So this must be in the same way, 90 minus alpha minus beta. Let me let you absorb that. No matter what, if I have a 90 and I have another angle, let's call it theta, the last one's got to be 90 minus theta. So that's why that's 90 minus beta. And that's why this is 90 minus alpha plus beta, which is 90 minus alpha minus beta. Yeah, we know so far. That is actually a very simple idea that just looks weird when you're using alpha, beta, all that kind of stuff. Now, just because, what's the angle in this dude?
Alpha.
Alpha. Kick ass. If you take the big dude, 90 minus beta, I told you we're going to have fun. 90 minus beta, and you subtract from it this guy, aren't you left with this dude?
Yeah.
So if you do 90 minus beta minus 90 minus alpha minus beta, well, the 90 and the beta cancels. Minus negative alpha is alpha. I'm going to post this online, but I have a finished product. I have several layers of this. I hope you understand. Dear God, if I write any more on this paper, I think we're all going to have our brains explode. So I have another piece of paper underneath that's got some summary of what we just done. Yeah?
The way those two triangles are also set up, it's a geometric identity that angle at the top has to be the same as the.
Oh, good. All right, good. There's other ways. I love it. There's other ways to work that alpha up to there. Kick ass. But I wanted us to get these 90 minus expressions just in general. Right? Yeah, that kind of thing happens often enough. Maybe. I think we've gotten everything we can get. Let me see.
Look at that.
Oh yeah, there's one more thing. Two more things, should be. Yes, good. All right. Let me see if I can. I just said I'm not going to write one more thing, but I will. Let's see if our brains explode or not. How long is this? What triangle is that in?
Alpha plus
It's the one that's got alpha plus beta in it, right?
Yeah, alpha plus beta.
I love it. So
Over
this
one?
is sine alpha plus beta. So what's this? Just right here. See how I can represent this. Cosine alpha plus beta. All right, let me show you the better picture here. All right, that's the same thing we did. So the first thing we did was write the sides of this triangle. But then I can look at this big ass triangle. It's just as easy because this hypotenuse is 1 also. So here's what we just figured out. Here's everything we just figured out. I'm going to let you absorb that for a second. There's our cosine alpha plus beta, because that's the x piece of the triangle that has alpha plus beta. Is that cool? If the hypotenuse is 3, this would be 3 cosine alpha plus beta. It's the percentage of the hypotenuse that's in that direction. This whole thing here is sine alpha plus beta. Because again, that's in the big ass triangle who's got alpha plus beta down there. Maybe. I can see a few more of you just checked out. That's right. Still got a few people trying desperately. All right, and did I forget this guy? No, we got this guy too, didn't we?
Yeah.
Yeah, sine alpha, cosine beta, and we got this whole thing is cosine alpha, cosine beta. All right, so we got all that kind of stuff. Now look what there is one addition. There's one thing I've added. This little line here. That's where things get interesting. All right. You see if I can work with those of you who are still with me. Just to absorb, right? This is nothing that you would have to do. I'm sure some of you guys are like, oh my God, he's going to give us this big freaky triangle inside another triangle, and I've got it. No. This is a little bit beyond what I expect you to do on your own. How long is this little dude here that I just drew?
Cosine alpha, cosine
And
beta.
let me really show you. I want you to realize why I want to know that. Why do I want to? Here's cosine alpha plus beta right there, right? There he is. And he's somehow related to this. He's a little bit smaller than this, isn't he?
Yeah.
He's smaller by this much. So if I knew what this thing was, I'd have an expression for what cosine of alpha plus beta is.
Sine A over sine B. Sine alpha over sine beta.
Not over.
Sine alpha times sine.
Beautiful. So this is the what for this triangle. Where's the right angle in this triangle?
It's right there.
Yeah, I'll tell you. That's right. I like it. It's right there, Jeff. So then this side has got to be. I'll turn this for my people that look at the trig correctly. Now it's in the base. So this has got to be the sine alpha piece of this, right? The y piece, when the angle's in the base, has got to be the sine of this times the hypotenuse. Maybe. Because what's sine again? Sine of some angle is y over, or h, or whatever. So what's y in general?
H times.
H sine beta. So if I just take this guy's hypotenuse, which is sine beta, times the sine of alpha, that's the y side. So this is sine alpha, sine beta. Crazy. And look here, here's sine alpha plus beta, this whole damn thing, right? So what side do I need to finish that? I have this. That's part of them. But I still need this side, and of course, what's that side going to be? There's hypotenuse sine beta.
Sine
With
alpha.
the little triangle?
This right here, the little triangle here. What's this base? What's this side here?
Cosine beta.
Yeah, it's going to be cosine alpha, sine beta. The cosine of that is the x piece of the hypotenuse, sine beta. Okay, I've got over half of you at least doing a good job of pretending like you're paying attention. And I knew going in this is going to be painful, this is going to be gross, this is going to be all that kind of shit, but I like the fact that some of you guys are kind of following. I'm not saying that you have to understand every damn thing, just make sure that you can see where some of this is coming from. Now I'm there. Let me show you, here's the last picture. I think we got everything. Yeah, here's the last picture now, showing what we just got. So what's an expression for sine alpha plus beta? It's equal to,
Alpha cosine
yeah,
beta.
so sine, I like that, alpha plus beta equals that plus this. Sine alpha cosine beta plus
Cosine beta.
cosine alpha
Cosine alpha.
sine beta.
Oh, that makes sense.
And what's cosine alpha plus beta? That's actually equal to,
Cosine alpha.
it's equal to this, that's too much. So minus how much?
Sine alpha, sine beta.
Sine alpha sine beta?
Yeah.
Now here's the way I remember this, because this is one of those you have to memorize. Yes. I would think sine is the nice guy. Look what sine does. Now see why this makes sense. And again, this is the way I remember this. You could have other ways to remember this. Sine's the nice guy. Oh, you're a plus? You'll stay a plus. Let's take turns. Sine and cosine. Let's take turns. Oh, sine's a nice guy. Cosine's the asshole. You're a plus? Screw you. You're minus now. I'm first. Cosine everything, and then you could be... That's how I remember that. So there's two levels of that. It's where the hell did it come from? Does it make sense where it came from? And secondly, just how do you remember it now? And that's the way I remember it, but you can come up with your own way. Now that you've said that, you might not be able to.
So use the sum difference identities.
Yes, here we go. You ready? So now we got to get the difference ones. And then I'll show you an immediate usefulness of this. It's going to freak me out. How are you doing that? That's good. All right, so somebody remind me, what's sine of negative x? Careful.
Negative sine.
Yes, why? Because sine is got odd symmetry. I love it. Take x. So sine of negative x is negative sine x. What's cosine of negative x?
Positive x.
Cosine of x. Because cosine has got even symmetry. So if you can put a negative input in, it's the same sign as it was for the positive input, right? This cosine goes like that more. Okay, so that means that I can look at sine of alpha minus beta. Now just using what we have right here. So that alpha is alpha, but what's this now?
Negative.
Negative beta. So wherever I see a beta, I have to put a negative beta. Are you guys with me?
Yeah.
If I put theta and 3 here, what do you just have, a theta 3 and a theta 3? So it's the idea of the form. You're just filling the form in with what you've actually got currently. So if I change the positive b to negative beta, then I've got sine alpha of cosine times cosine negative beta plus cosine alpha sine negative beta. And what is cosine negative beta? Cosine beta, right? Cosine doesn't care. It says, whatever, man, I'm always going to be the same. And he is. It's still an asshole. I like that. That's perfect. I didn't realize how far that went. And then sine is a nice guy. Oh, you're negative now? I'll be negative now too. So sine will change to minus cosine alpha sine beta. So again, sine is the nice guy. If he's plus, sine says, okay, you can stay plus. If it's the negative in there, sine says, okay, you can be a negative. So you can imagine what cosine's going to do, of course. Cosine, when it was plus, he made a minus. When it's a minus, he's going to make it a plus, right? So if you look at your little identity sheet that I highly recommend you have out with you when you're doing homework, but you better not have it anywhere near you when you're doing a test. Where are we? There it is. So that's where we are right now. That's what we just learned, and that's what you must memorize. So cosine changes the plus and minus, and he's always all about him first. So let's do a specific example that you don't need a calculator for. So say I want to do sine of 15 degrees. Now can you relate that as the sum or difference between two angles that you know the values for?
13 and 45.
Exactly. 45 minus 30 is 15. It's crazy. And of course we know 45 and 30. We know all the values for those. You with me?
Yeah.
So sine of 15 is sine of 45 minus 30 degrees. And now just fill it into the form that we just learned. All right? Sine is the nice guy. Sine says, I'll go and you go.
I don't understand how this is.
Sorry.
I don't understand.
So again, here's the, well, I don't like the way it's written there. Let's see. Here we go. Just goes a little further I want to. Right here, we're going to use this. This is the formula we just figured out here. Sine of alpha minus beta equals this. We just figured that out. How did we figure that out? Well, first off, we had to figure out sine of alpha plus beta, right? Now, is everybody cool with where sine of alpha, where these came from?
No, I'm still kind of stuck on the alpha that's up the top, and then the cosine alpha sine beta. That's kind of where you lost me.
All right. Right at that moment, tell me, because then I could do a lot more. But real quick, looking at this little triangle here. This side we'll call it x, right?
Okay.
Okay. What relates what I know with what I don't know? What trig function will relate those three things?
Cosine
Beautiful. So cosine of alpha equals,
equals x over sine beta.
all right, solve for x, you get cosine alpha sine beta. Coming out. Try to be out. Get it. And very similarly, the same thing for that side. That'll just be the sine piece, right? So the bottom's got the cosine in it, which makes sense, because that's the x piece. And then this has got the sine alpha in it, that's the y piece. And at first it didn't make sense why I made that little right triangle up there, right? You're like, yeah, now you're just freaking playing around. Don't involve me in your stuff. But now we see that here's sine alpha plus beta. Is that cool now? That little triangle?
Yeah.
Here's sine alpha plus beta, so it must equal this plus this. Period. Right? This side plus that side is just as long as that is. So that must equal the sum of those two. Similarly for the cosine, it must equal that side minus this side. That's where those identities came from.
Okay.
So for cosine, it has to equal this side minus that side. Now I want to show you a concrete, now we just went insane with alphas and betas and multiple things in a row. I want to show you a concrete example of the use of this. So I said, okay, what if we had sine of 15 degrees? Can you write that as the sum or difference of angles you know? And of course, it shouldn't be too hard to think, okay, I know 45 and I know 30, and their difference is 15.
So why did you make one sine and one cosine?
All right. Using the formula we just figured. Here's the formula we just figured out, right? Sine alpha, cosine beta, minus sine beta, cosine alpha. That's the thing we just figured out from the triangle on the other side.
Okay.
Cool. So we just figured out this here, right? We just talked about this here. And then if you plug in a negative beta, you'll figure out for the difference between two angles, you get this guy. Using the symmetries of sine and cosine. So when you plug in negative beta in, cosine stays positive,
Right. So
sine becomes negative, so that's bad. It's a minus in the middle now, right? So then I know that this here is true, period. So if I have sine of 45 minus 30 degrees, how can I write that now using my identity that I know is true because we just proved it?
Is that basically what you're saying? Is alpha is 45 and beta is 30?
And why would I say that? Because those are two angles that I know the values for, right? I know sine of 45, I know every freaking trig function of 45 degrees and 30. And 45 minus 30 is 15, which is the original question. What is sine of 15 degrees? So the one immediate reason why we just figured out addition and difference formulas is so I could figure out exact values for other angle values, besides 30, 45, 60, 90, 0. Right?
Without a calculator.
Beautiful. Exactly. Now, and I want you to realize, on one level you could say, well, the calculator would do that, and part of me says, well, yeah, that's great. This is not the only useful reason that we know these identities. Trust me, if you're going into Calculus 1, Calculus 2, trig identities show up almost any time you have calculus problem with a trig part in it. You want to know your identities, because maybe in this form it's easier to do something with than it is in that form. So if I had sine of x minus y, I can write it like this, and calculus is better able to handle this form. That happens so freaking awesome often in calculus. That's another whole reason why we want to know identity, so I can rewrite them in an easier to work with form. But this is the best example I can give for right now for a concrete example of this thing working. So sine of 15 is also known as this. And now that I've written as a difference of angles, I could use this identity. So how would this be? It would be sine of
45
45, right? Sine of alpha, sine of 45,
times,
cosine of beta,
which is 30.
30. So let this be a plug and chug. That's really all it is.
Minus sine of 30
Minus sine of 30,
times
cosine
cosine.
of 45. So everybody gets a turn, right? Sine gets a turn to each one, cosine gets a turn to each one. Sine's nice, so it keeps it minus in the middle. What is sine 45?
Square root of everything.
Beautiful. What's cosine 30?
Square root of everything.
Does anybody remember a problem that was almost exactly like this
Yeah.
in the homework? And they just didn't tell you at the time what the hell it was all about? Here it is. So what's sine of 30?
It's 1/2.
Good, so it's 1/2. What's cosine of 45?
Right, 2 over 2.
Rad 2 over 2, so you get rad 6 over 4 minus rad 2 over 4. And I think that one of the homework they made you square that bad boy, right? You guys see that? Now help me out. Somebody in the calculator, what is that approximately equal to? Careful now, you can't do square root of 6 minus square root of 2 is square root of 4, right? Nobody do that, please. Do you got it? Square root of 6 minus square root of 2, what is that?
Square root of 6 minus square root of 2.
Beautiful. Is that what the hell it is? It's not square root of 4. They're not like terms. So you have to do this in the calculator. Anybody get that for me? So,
0.259.
0.259. Now, using the calculator, what is sine of 15 degrees? It's crazy. All right. And of course, some of you guys are like, that does not impress me, Jeff. That just tells me that I should have used my calculator in the beginning. But again, realize that this is an approximation. I don't care how far you take it. When I say give me an exact value, I don't mean take it a few more decimal places out. Because if you want to go that way, then finish writing it out. No, it goes forever. Screw that. So when I say exact value, I mean this. That is the exact value. So if you're doing very delicate computations, where if you're off in the 18th decimal place on something, that means something's going to blow up, then obviously you want to use this everywhere until the very end. Because any rounding you do will screw you the hell over. Or whoever is sitting on that thing you're making. Let me turn it up. Right? It doesn't happen very often in engineering, but it's a kind of an extreme example. But there are definitely times you want to use the exact value, not the approximate. All right. So I know that was painful to go through the derivation, but can you see how to use the identities themselves? I mean, there's going to be several problems in 7.2 that are exactly like what I just asked you. Yeah, the very first set of problems, 3 through 14, gives you like sine of 15 degrees. So you got to rewrite it as the difference or sum of two other angles that you know everything about.
But you can choose them.
Huh?
You can choose them.
Yeah, exactly. So if I said sine of 75 degrees, how could you rewrite that? Come back down. There you go.
Or 40 plus 30.
Yeah. Sine of 40 degrees plus 35. Why did I do that? 45 plus 30. 45 plus 30. So it's just like the 15, just now it says sum. So it'll be exactly the same setup, except there'll be a plus in the middle, right? Whenever we write these. Yes, sir.
Why couldn't you just, I mean, with the sum, and I don't know if it makes that much of a difference, why couldn't I write it sine alpha cosine beta plus sine beta?
Yeah, I just did. That's the way I'm used to doing it.
Yeah.
I just,
Just to memorize it, it seemed to be easier.
that's the way I look at it.
Yeah.
But it's weird. I've noticed students don't look at it that way until now. So obviously, multiplying doesn't care what order you do it in. So this, see how I wrote this? Sine alpha, cosine beta, cosine alpha. On the handout, it's got cosine alpha first. Who cares? Whatever way sticks in your head better. And this stuck in my head better. Sine, cosine, and then the angle switch. Or you can do sine, cosine, and then the sine and cosine switch. I don't care. As long as you get this and this in it, you're okay. Doesn't change the value, of course, when you change the order of factors of the multiplication problem. Okay. Let's look at a few more homework problems to show you what they're going to throw at you. So they will give it to you in radians also, which is always very fun. Like this guy. So, I mean, one obvious thing you could do. Convert it to degrees if you want to, right? But at the same time, you maybe should be able to tease this out. Like if I sucked out of here 3 pi over 12, that would be pi over 4, right? Well, 3 pi over 12 plus 16 pi over 12 is this, isn't it? And what's 16 pi over 12? Reduce that. 4 pi over 3, which is something I know, right? You guys see? I mean, that's how you start. That's how you can tear this apart. Or just make it degrees. It doesn't really matter. I just want you to get used to these identities. But I do kind of want you got to get more and more familiar with radians also. Because why do you think radians happens a lot more often than degrees? And further
The
mathematics?
actual measurement.
It's the actual measurement. Yeah. Anytime angles are floating around by themselves, it's got to be in radians. Just like S equals R theta, those kind of formulas, it's got to be in radians. So that's why you try to get more and more familiar with radians. So this whole first section is just like that 15, sine of 15 and sine of 75 we just did. This section is just in reverse. That's even better. So like 15, can you put that back together?
Yeah.
What would it be involving? Addition or difference of angles?
Addition.
Yeah, it's a plus. It's a sine cosine. So it must have been
Sine.
sine of 18 plus 27. 45. It's crazy. So that's what I want you to do here is write the expression as a trig function of one number, sine of 45, and then find its exact value. All right, so you know it's going to come back together into something you know.
Is number 16 is a cosine.
Good. Cosine.
Plus,
You can
right,
tell
that's
it's going to be cosine or sine, because sine gives them both a chance. Cosine says me first. So I know it's going to be cosine of...
It's a plus though, right?
Exactly. Since it's a difference here, it would have started out as a plus, because cosine's the jackass. It says you were a plus, I'm going to make you into a minus. Nah. So it would have been the cosine of 90, which is?
0.
Okay. All right. You answer that faster than my Calc 2, which Calc 2 I'm always worried about. The quickest way to make your Calc teacher cry is to not know your basic trig stuff. So if they say cosine of 90 and somebody says 1, you'll see tears. If you want to see somebody cry, then you can make it happen. Now, on problems like this, this is related to one of the ones that don't make you memorize. So don't freak out and think that you're going to have to know it. So since there's a you can imagine, since there's a sum and difference formula for sine, sum and difference formula for cosine, there's a sum and difference formula for tangent. And they're also on this sheet, just at the very bottom, under the big black bar that says you don't have to worry about them. Because if I needed to know it, I've got sine and cosine memorized, and just get those, and then take the ratio to get tangent, right? There's no reason. If you want to memorize them, go right ahead. I don't mind if you memorize more. That was my sweater, Far Side Good Luck exam sweater I wore. My brain's full. Can I do? Some of you guys feel that way. So let's take, actually let's do this. We'll try a couple from this section. This is section 7.1. So you, in section 7.1, now here's the other thing you got to be careful about. When you're doing section 7.1 homework, you can only officially use what you knew by 7.1. So if you try to use a sum or difference formula here, it's no good. You didn't know that until section 7.2. You guys kind of with me? This is the way that math is going to work for you in the future too. You learn other things further down the road, but when you're doing homework, when you didn't know that, you can't use it. You have to use what you knew when you're in 7.1. When you get to 7.2, you could use that all day long, right? You guys understand? I mean, this happens. This has already happened to you, believe it or not. All right, when you learn quadratic formula, I don't know if your teacher made a big deal of it. Earlier, you weren't allowed to use it. You had to use factoring to solve a problem. You couldn't use quadratic because you learned that later. All right, so let's see. Let's try some of these. Ooh, I like 61. That one screws you. Was that me?
That was yours.
That's all right. That'll be an exciting. No, if it was, I'm dead. Oh, poor little dude. All right, there you are. Everybody with me? You trying on number 61? Put whatever letter you want to there. Take you 3 steps. Depends on which way you go with this. So let me point a few things out, because when you first start doing these kind of problems, you feel a little, you're not sure where to go. And that's just going to happen to you. And this is the way that a lot of math is. They don't have a problem like this in the examples. They don't. You have your identities that you know, and you have to apply them where they're appropriate. So what's one thing I told you that will help you? If you're working on one side, you can keep the other side as a reference point, right? That's where you want to be. So you could say maybe something would be interesting about that. There's a 1 up there, but 1 plus tangent squared, the best I could do with that directly. What is 1 plus tangent squared? Secant squared. And that actually would get you somewhere if you went a little further down that road.
How does 1 plus tangent squared equals secant squared?
So it's there's 3 of the most basic trig identities that there are. You must know at this point. Sine squared plus cosine squared is 1. If I took that and divided everything by cosine squared, I get tangent squared plus 1 equals secant squared. If instead I divided by sine squared, I would get
Cosine.
you get 1 plus cotangent squared equals cosecant squared. So I mean, I really.
That's
So
why it's right
if
there.
you start with sine squared,
Yeah.
unfreeze. Start with sine squared plus cosine squared. I'm not using you, just use whatever. If you divide everything by sine squared, What do you get?
1
1
plus cotangent
If you divide by cosine instead, cosine squared, you'll get 1 plus tangent squared equals secant squared. Those three you must know. If you're like me, you can memorize one. Memorize the first one, and then create the other two when you need them. But there are three identities. Now there are 7 identities, at least, right? We just added 4 today. Plus, plus, minus, minus.
Oh, I counted that at 2.
And then you have the even more basic stuff, the definitions of truth. All right, let's go back to this. Where are we at?
The tan
So, who's got a suggestion as to what to do?
work with the right side.
Work on this side?
Sure.
Kick ass. How does that side relate to what's down there on the other side? There's a 1 there, right?
Yeah.
So here's what I'm saying. Work with the side, but pay attention to the other side. Very often it will help you. Sometimes the other side will look nothing like that side. You're like, shit, let me just do whatever I can do. And this is where you guys have desperately got to develop the freedom, the confidence to just play. And to be wrong and be okay with it. I'll do some of these problems and I'll go, oh shit, that wasn't the way to go. And I got to go back up and start and try a different identity. Because that was a dead end. It's going to happen. You let it happen. You're getting closer and closer to real math. You're not there yet. So far, everything's been very regimented. It's specifically created to do certain things. Right here, you don't know which path is going to work. You just try something. So how would I make this become 1? Yeah, divide top and bottom by cosine squared. And what's going to come here? When I divide this by cosine squared, it becomes... Holy shit. It almost has to. When you see really good similarities between these, they're both ratios. The bottom's got 2 terms on it. It almost has to become this if you just force a piece of it to become what it's supposed to be. That is it doesn't always work. You gotta be careful. But that's the first damn thing I try is, there's a 1 there, not a cosine squared. So let me divide cosine squared, top and bottom. What would the top become if I divided by cosine squared? Exactly. Where'd it go? There you are. So this is so working with this side. If I divide by cosine squared, I get secant squared over 1 minus tangent squared. And of course, secant squared is 1 plus tangent squared. So I've proven it. That's it. That does equal that. Bam. So part of 7.2, I want you to realize this. And in 7.3, we're going to do the same thing again. Part of 7.2, we just learned new identities. We learned sine of alpha plus beta and so forth. So they're going to have a whole section like this where they're going to have those in it. Section 7.3, we're going to learn some other identities. They're going to have a whole section like this, prove the identities, where they're going to have those new identities in there. You see how that pattern develops?
No. Yes.
Y'all look appropriately excited about that? Yeah! Alright. I'll see you guys tomorrow. Yeah.
Go back to that one real quick.
Alright, so this is the way I did it myself.
I get it, I'm just saying, I can see how.
That's the way I did it. I did it a different way. But the way we just did it, pretty good. I love it. So you're done. There you go. That's one of the 3 signs. Exactly. So one of the 3 ones you have to know. That's what secant squared equals. Oh. Yeah. Well, what's 2 plus 2? How did you change it into 4? Because it is 4. You see what I'm saying? So if I have an expression, that's what I meant. If there's a simpler way to write it, I'm going to write it in a simpler way. So
I was just wondering how, when it was underneath, when you put it back over, it became secant.
So if what I have to do to go ahead top and bottom, I have to divide what's
Okay.
1 divided by secant squared.
Okay. Good thing is that I can.
So I get
After this, or,
It's on the line. And then I think it's great.
So you turn in your check, there's on it, so that's
I knew it, but the year, my son.
Oh, your old test.
It was like.
You didn't get the that's back. Right.
Like there for the rest of your life.
So when I handed out stuff, the test corrections were part of what I did. Okay, so I gotta find it.
And of course I
Just shoot me an email or something so I can look for them. We might have just snuck into another class. Correct. Yeah.
I didn't want to get the book.
so since I didn't know that we could actually use the law of signs